The final application of calculus that we need to look at is volume of revolution. What we do here is take the area under a curve y equals f of x and rotate it about the x-axis. We complete one revolution and we end up with a solid. To find the volume of this solid, we could imagine dividing it up into many small segments, each with thickness delta x, a small value. So we're slicing up the solid and it looks something like this. So what we're looking at here is a disk known as the elementary disk. The thickness is delta x and the radius is y, which is the height of the curve at that particular point. So if we have a disk, let's just look at this disk taken out on its own. So delta x is this distance and the radius is y. Now the disk is a very thin cylinder. So the volume would be the area at the end multiplied by delta x. And this is why we have to take delta x very small, because we're imagining this is a cylinder. If you take it much thicker, then obviously you're not getting a cylinder because the radius here is not the same as the radius there. So delta x needs to be really thin. So this is pi y squared dx. And the volume, the total volume, will be the sum of all of the segments. So to get the total volume, we're adding up all of these disks right the way across from x equals a to x equals b. Now, in the limit, as delta x tends to 0, the sum becomes an integral. So we get the integral from a to b of pi y squared dx. Pi is a constant, so we can slide it outside. So we normally do pi times the integral from a to b of y squared dx. We can see this idea quite nicely by using autograph. So I've got a curve in here, and I'm going to try and work out the volume of revolution between 0 and 3. So I'm going to take this area here and rotate it around. So what I'm going to do is click on Find Area, and I'm going to find the area using rectangles. So I'm going to start with just 10 of these rectangles, so it's going to be very approximate, this one. And we want that whole area from 0 to 3. So we can see we're using this as an estimate of the area. But I can now click on this and find volume. And what will happen is it will do this rotation around, as we can see, and it's filling that volume with all the disks that we talked about before. Now we can rotate this and have a look, and we can see that it is very approximate, but of course we can get that much better by taking more of those rectangles, which is the whole calculus type argument. Now I'm just going to snip that picture because I want to use it shortly. So we'll just snip that picture and we'll grab hold of that again later. But let's just try changing to more of these. So if I put in 100, it should now be a very good approximation. So first of all, it's going to give me the area, and then it's going to rotate that around. And you can still see that it's made of these discs. But if we have a look now, that volume fits very, very well under the curve. So here is the snip we used when we did the animation on autograph. So it's quite clear that each of these is a cylinder. Now, in this particular case, we went from 0 to 3 with 10 of these. So the thickness of any particular one is just going to be 0.3. When we did it with 100 a bit later on, then it would have been 0.03. So the thickness is 0.3, and if we drew the disc out, we took it out of there, then the radius would be the height of the curve at this point, so the distance from the axis to the curve there. And we've talked already about how to work out the volume of this cylinder. You work out each individual one, add them up, and you get the approximation. And the approximation gets better and better as you use more of these discs. And the calculus argument is, of course, for this particular one, we'd integrate from 0 to 3, pi y squared dx. So if we know y in terms of x, we can do the integral and work it out. And the calculus argument is that we're using an infinite number of infinitesimally small cylinders.